All right, time to take a little pause. Let me show you guys. You're kind of getting ready for college, so I want to show you a way to impress people of the opposite gender with your math prowess. Yeah. So take a look. Shut those down for a second. You can do that at home. I want to talk to you about differentials. This is pretty cool stuff, and it's not hard. So here's kind of what we did the other day. Remember, we drew this picture. We drew that picture, right? And we just said if we've got some function and we want to approximate how much the function is changing for a given change in x, we call that delta y. Well, we could approximate that with a differential, right? Just a linear approximation. So we're going to take the tangent line to the curve at c, and then we're just going to look at how much the tangent line changes. And as long as we're close to the point of tangency, the tangent line matches the curve fairly well, right? And how well does it match it? Well, we'll actually look at a way to determine if it works well or not. So here's the book's picture, kind of the same thing, right? There's the light blue line is the tangent line, there's the function, there's your delta y, and there's your dy, right? And really what this comes down to is just remembering that dy, which is what we call the differential approximation, is just f prime of x dx. But that's so simple because that's the definition of a derivative, right? If we think about this in terms of what a derivative is, right? I mean, we know that this is such an easy thing to remember because what are two ways to write a derivative? Well, you can write it in ratio form, which is the same thing as saying f prime of x. Multiply each side through by dx, and what's that give you? dy equals f prime of x dx. How about that? Well, there's the definition of a differential, right? Matches our picture. Calculus gods are wise, aren't they? Okay, so let's try this. Let's just show that this works, and it's really simple. So if we've got some function y equals x squared, and we want to find the approximate change in the function when x is 1, and we're going to tweak x, we're going to nudge x by 0.01. Okay, so that's dx. Okay. All right, well that's easy, right? We know that the differential dy just equals f prime of x dx. Well, what's our function? X squared. So f prime of x is what? 2x. Ah, okay. So then this is just equal to 2x dx. Well, what are we going to plug in then for x and dx here? Yeah, we're just plugging in 1 for x, and dx is 0.01, right? So the approximate change in the function is 2 times 1 times 0.01 equals 0.02, okay? Well, let's compare that to the actual change in the function. Okay, the actual change in the function is just going to be what is f of 1.01 minus f of 1, right? Everybody agree? So delta y is actually equal to f of 1.01 minus f of 1, which is just going to be, 1.01 squared minus 1 squared, right? And so we'll put that in our calculator and see what we get. Okay, so then 1 squared is just 1, right? So 0.0201. So what's that tell us? Well, it tells us that the differential approximation is pretty good, right? This differential approximation is really just saying, if I combine these two things, that's really just saying that delta y is approximately equal to dy, which is 0.02, right? Okay, let's use that to our advantage. Well, one thing we do with this a lot is we're going to make quick estimations of air propagation. Okay, we talk about that a lot in physics, right? So if we're going to propagate an air, like for example, let's look at it this way. If we were going to build a cube, let's say we're going to mill a cube out of metal, and there's going to be a certain tolerance for how well we can measure, how accurately we can measure the length of each side. Let's say we can measure it to within 1 millimeter, 1/100th of a meter, or 1,000th of a meter, right? So if I can measure that to within 1,000th of a meter, does that mean that the volume that we would be building, the volume of the cube, would be good to within 1,000th of a cubic millimeter? Doesn't, does it? Because that air is going to be propagated, because when I calculate the volume of the cube, I'm going to multiply that faulty measurement by itself 3 times, right? You see what I'm saying? So small errors in measurement can be propagated to be bigger errors in other quantities like volume. Does that make sense? Okay, so then we want to be able to use this idea to kind of gauge what's the propagated air going to be. So if we think about it this way, we've got some function. If x is the measured value, right, then the actual value is going to be x plus delta x, because there presumably was some error in that, right? Okay, and if I take the difference of those two things, that's going to be the change, the actual change in the function, right? Based on whether we're using the measured value, which for us was 10 centimeters, let's say, or the actual value, which could have been off by a little bit, right? It could have been plus or minus a millimeter, so it would have been 10 plus or minus 0.001, or it was 10 centimeters, so 10 plus or minus 0.1 if we're talking about centimeters first, right? Does that make sense? Okay. So then what if we want to do a problem like this? Say we measured the radius of a ball bearing to be 0.7 of an inch, right? If the measurement is correct to within 0.01 inches, estimate the propagated air in the volume V of the ball bearing. Okay, so let's, first of all, what's our formula for volume? Volume of a sphere. 4/3 pi r cubed. Okay, good. So we know that this is r, and this is going to be delta r, isn't it? Yeah. Right? That's going to be the amount that we're off. Delta r or dr, same thing, right? So this is r, and this is delta r or dr. Okay, how much that's changing. But we want to estimate how much the volume is going to be pushed one way or another by that air in measurement, right? So really what we're trying to find is, what is delta V? What's the change in the volume that's going to be, the volume calculation that's going to be propagated by this little air in the measurement of radius, right? So that's going to be approximately equal to dV, and what's dV? It's going to be V prime dr, right? Yeah. Okay, so what is V prime?
4 r squared.
Right?
Oh my gosh.
So then dV is equal to 4 times pi times 0.7 squared times dr, which I'm actually going to write as plus or minus 0.01. Okay? So what's that give us for an answer? That's gonna give us an answer. We can plug that into our calculators. Let's see. Oh yeah, it's way more simple than if you had to calculate this the other way. Yeah, well we will. This is, you'll get a reward. This will be one of those that's not hard. So we'll do 4 times pi times 0.7 squared times 0.01 gives us that. Okay, so the propagated error is going to be, the estimation of the propagated error, is going to be plus or minus, exactly.
Plus or minus 0.06.
Yep. Is going to be plus or minus 0.062 roughly, right? And the units would just be cubic inches, right?
Oh my gosh, that's great.
Right? Okay, but then the question arises, okay, that's useful, but really what's more useful is knowing, is that good or bad? Is this tolerance acceptable, right? And so there's one other thing we could do. Well, if we're trying to know if this is good or bad, we want to be able to express this propagated error as a relative value compared to the actual volume calculation, right? So really what we're looking for here is something like, oh, darn it, I'm not going to do that. Jeez. Relative error is going to be given to us by, or it's going to be approximated by dV over V, right? So you might be thinking, well, let's just plug this number in, right, for dV and compare that to V, but we can take a shortcut there too, because look what the formulas are. dV is just 4 pi r squared dr, and V is 4/3 pi r cubed. Look at all the stuff that cancels. The pi's cancel, I can cancel an r squared, and I can even cancel a 4. So I end up with 1 over 1/3 is 3 dr over r. It's a pretty simple formula, right? So we just end up with, then we could just plug in dr is plus or minus 0.01, r is 0.7, right? How about that?
I like that.
That's pretty simple.
You see.